Welcome back, everyone. And today we're going to continue the video series on the ultraviolet catastrophe. So in the last video, we landed on this equation here, which motivates us to think about n, which is the number of modes in the cavity. It motivates us to think about it in terms of sort of nx, ny, and nz coordinates. And moreover, it's something I didn't mention, but this is an equation of a sphere. Okay. So that's going to motivate us even further to try to establish a sort of quantitative way to look at this quantity, little n. So the next thing we're going to do is we're going to look at this space, which we've already said is valid for nx, ny, and z being greater than 0 or equal to. And what we get is we want to find an n, capital N, total number of modes that's going to be roughly equal to the volume. Okay, the volume of this space. It's going to be the volume of this space, which is 4/3 pi n cubed. Okay, because n is like the radius, as we discussed in this space. And then there's some other factors we need to take off, right? So we already discussed how this thing is only it's only 1/8 of the total space. And if I were to try to roughly sketch that in, I'm going to redraw it because I drew that last graph was pretty poorly drawn. But the 1/8 factor comes from the fact that if you have a space, okay, this is nx, ny, and z. If you have a space and we're only assuming the positive front quadrant, actually I don't know if I can call it a quadrant, whatever 1/8 of something is, there's going to be these other spaces which we can't use because they're not valid. N has to be positive integers, right? So there's one there, there's one back here, there's one there, and then there's also going to be 4 more cubes on the bottom, if that makes sense. So overall, we only get this 1/8 factor. In addition, we're going to add a factor of 2 here, and I might talk about this a little more. But this is solely due to the fact that electromagnetic waves have 2 possible polarization states. So this is definitely something that I think deserves more attention and more discussion. But in general, for traveling electromagnetic waves, let's say you had a wave, let's draw it over here. Let's say you had a wave traveling in this direction and was going through vertical polarizers, vertically oriented polarizers. Then the wave can travel if it is in fact vertically polarized, okay? And there's a magnetic component too, I'm not going to draw it. The other polarization state for this same system in this orientation would be in the other direction, polarized, okay? And that would pass through a horizontal polarizer. So this is why you get this factor of 2. Once again, I think it deserves more discussion because for standing waves, this argument sort of falls short. But what we realize is that polarization is a property. Okay, it's a property of photons. It's not this is a sort of observed phenomenon, and we can observe it with traveling waves very easily. But polarization is a property of photons. Okay, so now that we have capital N, we should ask, what is capital N? Capital N equals the total number of modes in the cavity. And it's important because it tells us, we're going to be getting into a little bit of sort of statistical mechanical stuff soon, but it tells us the number of configurations of that wave in that cavity. Okay, so the number we get, just to rewrite it, it's going to be 1/3 pi, 1/3 pi n cubed. And n, we've already defined it as, n is going to be 2L over lambda. 2L over lambda. So we get 1/3 pi 2L over lambda cubed, which is 8/3 pi L cubed over lambda cubed. Okay, so we discussed in the beginning that we figured, or we assumed, that there was some relationship between the number of modes in the cavity, the wavelength, the length, and even furthermore the frequency and the speed. These quantities are all related in this type of problem. Okay, so and this is another big step. So what we need to do next, now that we have this total number of modes, on its own is not super useful. But at the time, what they did is they used the equipartition theory. Okay, and we've seen this a little bit before. And I'm going to put the link up to the video on the top there. But we did a video that showed for Newtonian systems that if you have just particles floating around in the box with no potential field, we showed that the average energy was equal to 3/2 nkt. This really is an application of the equipartition theory. And what we're going to do it now is we're going to do it for an oscillating system where there is a potential field.